Hello, my name is Stella and we're the 3D Clouds for Climate Extremes team. In late August 2019, Hurricane Dorian was a Category 1 storm in the Caribbean and was forecasted to remain weak as it traveled north. Unexpectedly, it was rapidly intensified to a Category 5 superstorm and became the strongest storm on record to hit the Bahamas, causing widespread destruction and the loss of 200 lives. Forecasts of Hurricane Dorian were notably poor, not only in predicting its rapid intensification, but also in tracking its path, which was unexpectedly uncertain. As a result, people in Bahamas had very little time to prepare for the storm's devastating effects. And this challenge isn't unique only in Dorian. Predicting the intensity of tropical cyclones in general remains difficult. One key reason is that cyclones are poorly resolved by operational forecasting systems. Microphysical properties such as ice water content, which play an important role in the intensification process, are not represented well in forecasts. On top of that, we have very limited direct observations. Only about 80 to 90 cyclones occur globally each year, and even fewer are directly measured. What we want to do here is to reconstruct various microphysical properties of the clouds in 3D. The radar reflectivity shows the density of the clouds, and this is an indicator of the rainfall. Ice water content has been found to be higher in rapidly intensifying cyclones. Additionally, droplet effective radius is important for how the cloud reflects sunlight and trap heat. Ideally, we would like to have continuous direct observations of tropical cyclones from sensors capable of penetrating clouds. Unfortunately, this is not the case, and even when such data is available, it's typically limited to 2D. To truly understand tropical cyclones and improve our ability to predict them, we need to complete 3D reconstructions of their cloud structure. And now I will hand over to Caesar.
Thank you, Stella. And now let's talk more about the dataset that we built. First, our primary input data are the geostationary satellites. Sensors like GOES have two main properties. The first one is they have a high temporal resolution. Basically, you can expect one image every 10 minutes. And the other one is they have a super large and constant field of view. For GOES, for example, as you can see in this slide, it covered the whole America. In our work, we achieve a near global coverage by combining three geostationary satellites, GOES, MSG, and Himawari. And together they will permit us to study clouds across the America, Europe, Africa, and the Asian Pacific region. Okay, geostationary data is kind of great because, but they are limited to observing only the top of clouds. For understand better the vertical cloud structure, we can complement them with satellites like CloudSat, which provide detailed vertical information of many different properties like radar reflectivity, ice and liquid water content, among others. Here in this slide, you can see how CloudSat orbits overlap with the geospatial, geostationary field of view. I think now we have a better understanding of the main component of our data set, but to make possible this 3D cloud reconstruction, we adopt a two-step approach for data preparation. First, we create a large data set of geostationary images for pre-trained our models. And second, we fine-tune these models using a data set where geostationary and CloudSat observations are collocated. In this way, we can maximize the strength of both data sources. Finally, we also develop a benchmark dataset specifically for tropical cyclones by integrating our previous sources with the timing and location of the cyclone events. In that way, our models can be fine-tuned only for tropical cyclones, improving performance for this specific downstream task. And now Lily will share more details about the deep learning framework.
Thanks, Caesar. So let's have a look at our machine learning task. We train our models to predict the 3D distribution of the atmosphere from geostationary satellite images. It's not quite that easy though. Since we want global 3D observations, our models need to make predictions from multiple satellites, which have sensors with different spectral and spatial resolution. So how do we achieve this? We create a sensor-independent model by pre-training an image model to reconstruct masked versions of observations from a large geostationary satellite dataset. First, our model creates wavelength encodings, which makes our image encoder sensor-independent. It's also geospatially aware, using time coordinates and solar and satellite angles to improve prediction accuracy. Here you can see what this pre-training task looks like. The model receives a masked satellite image as input and has to fill in the missing pixels. After pre-training, we replaced our image decoder with a 3D decoder to predict the three-dimensional structure of our atmosphere. Our model can simultaneously predict multiple variables, including radar reflectivity, ice water content, and the effective radius. Here's an example of the vertical profiles from our model. The top row shows radar reflectivity, ice water content underneath, and then the effective radius at the bottom. As you can see, our model predicts all three variables well, including the structures within the clouds. One of the goals of our project was to make predictions across the entire globe. With the 3 satellites we've trained on, we already cover a large part of the globe. And because our model is sensor independent, we can include satellites which it hasn't seen during training to get complete global coverage. Our model can make predictions just as well using these new satellites, allowing us to produce global, 3-dimensional cloud maps. And now I'll hand over to Shireen, who will tell you more about our predictions for tropical cyclones.
Thanks, Lily. Yeah, we can take a look at one of the cyclones in the North Atlantic here. Specifically, let's go back to Hurricane Dorian, which Stella introduced in the beginning. This storm made landfall in the Bahamas as one of the most damaging Category 5 storms in history. For Dorian, we have 2 overpasses from CloudSat, one before the storm intensified and one after it already made landfall. Both overpasses are pictured here. What we are missing is a direct observation of the storm while it was undergoing rapid intensification, going from Category 1 to Category 5 within 3 days. In particular, in this period, forecast models missed that the cyclone had already developed an eye wall. With our 3D cloud reconstructions, we can use the 10-minute frequency of geostationary imagery, which sees the cyclone from the top, and reconstruct the cyclone in 3 dimensions. In the animation, you can see the storm at its peak intensity, our model clearly showing the eye of the storm. So as Stella mentioned in the beginning, predicting cyclone intensity accurately is difficult for many reasons. But with our 3D cloud reconstructions, we have created a huge data set of high-resolution reconstructions of cloud properties. We're now able to continuously monitor tropical cyclones in 3 dimensions, which could improve our understanding of the intensification of tropical cyclones. With this information, we can create more reliable early warning systems that help populations stay safe in extreme environments. And with that, that's it from our team, and I will leave you with the final animation of Hurricane Dorian. Thank you.